Hello, welcome to my channel. This is an educational channel where we learn about different important items that you may not know anything about. And today is video 185 on the reciprocal system of theory from Dewey B. Larson. Mr. Larson derived the reciprocal system back in the 20th century and eventually came out with his fundamental postulates in the 1950s, and after that wrote books until his death in 1990. We're looking at his 1979 book here called Nothing But Motion. And the basic idea behind the reciprocal system is that we do live in a universe of motion. Not a universe of matter, not a universe of energy, but a universe of motion, where motion is the prime constituent of the universe, and motion is the relationship between space and time. Space and time are not the container of the universe, but they are the contents of the universe. Motion is basically a fraction where space and time is the numerator, and time or space is the denominator. And that sets up a generalized reciprocal relationship between space and time. And but it is a bit more complicated than that because space and time are both multidimensional, meaning coordinate. They have their three-dimensional aspects. They also have their scalar aspects, their clock aspects. Time is always getting later and later and later. That is the flow of time. And space is always getting farther and farther and farther apart as the flow of space. And space and time also both come in discrete units. There's a minimum unit of time and a minimum unit of space. 1 unit of space in 1 unit of time is the speed of light. That sets the speed of light up as being not the maximum speed of the universe, which is what Einstein says, but as the midpoint of the universe, with really two separate universes or sectors of the universe. Larson calls those the material sector, that is the sector that is moving slower than the speed of light, which is the one that we're familiar with. But there's also what Larson calls the cosmic sector, wherein everything is moving faster than the speed of light, and the speed of light is actually the minimum speed of that universe. Now, the cosmic sector is something that legacy science knows little or nothing about, but because of the reciprocal postulate, meaning that there's a reciprocal relationship between space and time, what we know about the material sector can be extrapolated to the cosmic sector. All we have to do is invert the roles of space and time. So if something is in the material universe, its exact mirror image is also in the cosmic universe, with the caveat that you just have to invert the relationships of space and time. Okay, now we are going through chapter 12 of this book, Nothing But Motion, which is primarily on atomic physics. And this chapter is called Basic Mathematical Relations. And we're going to go back a little bit and kind of try to go over some of the mathematical relations. Here in this chapter, he's really defining a lot of the various a lot of the various physical and mechanical properties of things, and how that everything can be described exclusively in terms of space and time. Now, I just want to mention that, where you have atoms and subatoms and so on, these are combinations of motions, and everything is a certain kind of motion. You have really 4 kinds of motion. You have your translational motion, you have your vibrational motion, you have your rotational motion, and you have your rotational vibration. And those are all can be in 1, 2, or 3 dimensions, or at least two, and those different motions can combine in various ways to create the different atoms on the periodic table, as well as the different subatoms. Okay, we're going to go back here and start right here in the middle of this paragraph. However, the atom rotates in the inward scalar direction. Now, just remember, scalar motion is a motion that has a magnitude, but it has no direction. Okay, so it's either inward or outward. And you can envision this by using a balloon, and you put some dots on the balloon with a magic marker. You blow up the balloon, and all the dots are moving away from each other. That is an outward scalar motion. If you suck in the balloon, all of the dots are moving toward each other. That is an inward scalar motion. That outward scalar motion at the speed of light is what Larson calls the progression of the natural reference system. That is the flow of space-time. That is always there, the progression of the natural reference system. You get to gravitation, or the inward force that creates the atoms, if you don't want to use the term gravitation, which Larson uses, by first nullifying that outward progression, first of all, and then adding another negative or inward motion to that. And so that's kind of what he's getting at here. The atom rotates in the inward scalar direction, and inward motion necessarily takes place in opposition to the omnipresent outward motion of the natural reference system. Two inward displacement units are therefore required in order to reach the limit of one net unit. These two units extend from unity in the positive scalar direction, what he calls the positive zero in terms of the natural system or the natural reference system, to unity in the negative scalar direction, which he calls the negative zero. So, that goes against basic math that you might have learned, that there is both a positive zero and a negative zero. And they constitute the maximum for any one-dimensional unidirectional motion. In three-dimensional space or time, there can be two displacement units in each of the three dimensions, and the maximum three-dimensional unidirectional displacement is therefore 2 to the third, or 8 units. There have been some suggestions that the number of possible directions and consequently displacements in three-dimensional space ought to be 3 times 2 equals 6, rather than 2 to the third power equals 8. It should therefore be emphasized that we are not dealing with 3 individual dimensions of motion. We are dealing with 3-dimensional motions. The possible directions in a 3-dimensional continuum can be visualized by regarding a 2-unit cube as being an assemblage of 8 1-unit cubes. The diagonals from the center of the assemblage to the opposite corner of each of the cubes then define the 8 possible directions. And so if you know your geometry, or even if you don't, you can just try to envision that, try to visualize a cube that you divide into 8 cubes by, basically the cube is 2 units on each side. And so basically dividing each one of the sides in half, so you have 8 1-unit cubes. And then he says the diagonals from the center of the assemblage to the opposite corner of each of the cubes then define the 8 possible directions. These would all be well, when you have a cube like that, you also then have a star tetrahedron, and these diagonals would be like the altitudes of the star tetrahedron, or of really the several star tetrahedrons that you would have there. An important consequence of the fact that these are 8 displacement units between the 0 point of the positive motion and the end of the second unit, which is the 0 from the negative standpoint, is that in any physical situation involving rotation or other three-dimensional motion, there are 8 displacement units between positive and negative magnitudes. A positive displacement x from the positive datum is physically equivalent to a negative displacement 8 minus x from the negative datum. This is a principle that will have a wide field of application in the pages that follow. The key factor in the relation between motion in space and motion in time is the previously mentioned fact that in the context of a spatial reference system, all motion in time is scalar. And in the context of a temporal reference system, all motion in space is scalar. The regions of motion in time and motion in space therefore meet in what is essentially no more than a point contact. It follows that of all of the possible directions that a motion in time can take, only one of these time directions brings the motion in time into contact with the region of motion in space. Only in this one direction can an effect be transmitted across the regional boundary. Inasmuch as all possible directions are equally probable, the absence of any factors that would establish a preference, the ratio of the transmitted effect to the total magnitude of the motion, is numerically equal to the total number of possible directions. As can be seen from the foregoing explanation, the transmission ratio depends on the nature of the motion, particularly on the number of dimensions involved. However, the value with which we will be most concerned is that applicable to the basic properties of matter. This is the relation that was called the interregional ratio in the first edition, and it appears advisable to retain this name, although the more extensive information now available shows the relation is not as general as the name might indicate. On the basis of the theoretical considerations discussed in the preceding paragraphs, there are 4 possible orientations of each of the two-dimensional rotations of the atoms, and 8 possible orientations of the one-dimensional rotations, making a total of 4 times 4 times 8 equals 128 different positions that a unit displacement of the scalar translational motion of the atom can take in 3-dimensional time. In addition, each of the rotating systems of the atom has an initial unit of vibrational displacement with 3 possible orientations, 1 in each dimension. For the 2-dimensional basic rotation, this means 9 possible positions, of which 2 are occupied. So that's for the 2 photons that are at the core of each one of these atoms. Each of the rotating systems of the atom has an initial unit of vibrational displacement. This vibrational displacement is the photon. Okay. For the two-dimensional basic rotation, this means 9 possible positions, of which 2 are occupied. Thus, for each of the 128 possible rotational positions, there is an additional 2/9 vibrational position, which any given displacement unit may occupy. The interregional ratio is then 128 plus 128 times 2/9, which equals 156 in 4/9, or 156.44. Now, you have to go over this derivation probably repeatedly to understand where he's, all of the numbers and how he's employing this. But to just know at this point that he uses this interregional ratio very commonly. And so, if you're wondering where he's getting it from, this is where he's getting it from, chapter 12 of Nothing But Motion. And so when he starts to use this, don't just say where's he getting this from? This is where he's getting it from. And this unit is also modified if you're using a subatom, because within subatoms there's only one photon or one vibrational displacement. And so instead of using 128 plus 128 times 2/9, which is 128 times 11/9 is what we're really talking about. In the situation with subatomic particles, you have really 128 plus 10/9 instead of 11/9, and that turns out to be 142.22, or 142 and 2/9. So he uses that number as well in other situations. It is this, again, this is a process of Larson deriving a theoretical universe strictly from the postulates that he postulated back in the 1950s, and then he developed them through a process of deduction. If this, then that. If this, then that. And then I did about 15 videos on that earlier, going over his talk that is called The Outline of the Deductive Development of the Reciprocal System. It has about 165 different steps that he takes to derive all of this stuff. And so he derives a theoretical universe, and then he compares that universe with the universe that the mainstream scientists have measured and have observed. Okay, now it is this interregional ratio that accounts for the small size, sizes in quotes, the small size of atoms when the dimensions of these objects are measured on the assumption that they are in contact in the solid state. According to the theory developed in the foregoing pages, there can be no physical distance less than one natural unit of space, which, as we will see in the next chapter, is 4.56 times 10 to the minus 6 centimeters, or 4.56 times 10 to the minus 8 meters. But because the interatomic equilibrium is established in the region inside this unit, the measured interatomic distance is reduced by the interregional ratio, and this measured value is therefore in the neighborhood of 10 to the minus 8 centimeters or 10 to the minus 10 meters. So what he's showing here is that this interregional ratio is basically the amount that you're losing in the translation if you're trying to measure across a unit boundary. Okay, when you're trying to measure across the unit space boundary, 1 unit of space, if you're trying to measure into from the sector that we're in, which is multi-units of space, if you're trying to measure into the area that is less than 1 unit of space, you have to reduce all your measurements by the interregional ratio. He says, but because the interatomic equilibrium is established in the region inside this unit, the measured interatomic distance is reduced by the interregional ratio. Okay, so so that's what you're losing in the translation. What you're measuring is one thing, but what you're actually observing is another. The measured interatomic distance is reduced by the interregional ratio. The inversion of space and time at the unit level also has an important effect on the dimensions of interregional relations. Inside unit space, no changes in space magnitudes can take place, since less than unit space does not exist. However, as pointed out earlier, the motion in time, which can take place inside the space unit, is equivalent to a motion in space because of the inverse relation between space and time. An increase in the time aspect of a motion in this inside region, the time region, where space remains constant at unity, from 1 to t, is equivalent to a decrease in the space aspect from 1 to 1 over t. Where the time is t, the speed in this region is equivalent space, 1 over t divided by time, t. So 1 over t to the second power. So an increase, as pointed out earlier, the motion in time, which can take place inside the space unit, is equivalent to a motion in space. Okay, so inside a unit of space, space does not exist. Only time exists. And inversely, inside a unit of time, only space exists. But we only see space. We do not see time. And so when we measure something that is in time, we convert it to what is the equivalent in space. And in this case, you have to use this fraction 1 over t squared to basically convert what we see in the time region. We will go over this again tomorrow, but I know that this is super abstract and difficult to manage, especially when you're not really being given any specific examples to illustrate. But this is important stuff to understand the reciprocal system and really understand where Larson's coming from, what he's thinking about, what the theory is kind of founded on. So we'll review this again tomorrow. But thanks for tuning in for now, and have a great day.